Physics 30s, we're going to do our answer key for the pretest. So as I go through this, mark it correct, mark it wrong. If you have any questions, or correct your mistakes, if you have any questions about any of these answers, come check out my Google Meet, right? Ask me questions there. Try to refrain from asking these questions through email, unless they're after Google Meet hours or regular class time hours. Most of the time, I'm pretty good at answering them outside of class time. If not, come to those Google Meets. The Google Meet will be open up from like 9 until 3:30 or 4, whenever I'm sitting at my desk. It doesn't really matter. Come pop your head in and ask some questions. I have this ability to write on this page here during my Google Meet as well. So you can see I can go through some of these questions with you in more detail. That might be a bit harder to do through an email, through text. All right. Some of the lucky few have actually gotten video responses to some questions. Can't do that all the time. So it's best if you just come to the Google Meet. I'm okay with repeating a bunch of questions over and over again if I have to. Yeah. Anyway, beside that, let's get to the answers to this key here. So positively charged rod is brought near to, but does not touch. Very key, right? One end of a neutral metal rod. So we got this nice little metal rod here. It's on an insulating stand, which just means that if I charge this rod, it's not going to lose its charge because the charge can't pass through the insulating sphere or insulating stand that we have here. Okay, so there's going to be a positively charged rod coming near this. Don't know which I want to put that on, so let's put it on this side. So here's my positively charged object. So as it gets closer, it's going to draw all the negatively charged electrons through the conducting rod, and it's going to leave the positives where they were. So let's just say that's how many positives there were, right? One end of the rod is then going to be grounded. Okay, so let's ground this off. So now, if you see this key during the static one, you're not going to see me ground this and disground it, but it doesn't really matter. You'll see what happens here. So I'm going to ground this, okay? By grounding it, it's allowing more electrons from the Earth to come up, because you can see here there's a big positive piece at the end of this rod, so electrons are attracted to it. They're also attracted to the positive piece. I'm sorry if you can't see my cursor. Positive piece at the end of the rod, and they're also attracted to the positive object that's over here as well. So there's going to be electrons traveling up through this wire and depositing themselves on this object. Some of them going towards this piece over here. And then what's going to happen is I'm going to disconnect the ground. I'm going to follow the rules. The ground is removed. Then the positively charged object's removed. And you can see that now there's way more negative up here. Way more negative. So that means I'm going to have a negatively charged object overall. And there we go. Now, just 1 second to see. So I can answer email. Okay. So we'll have a negative. That's true for most of these charging by inductions. If you charge by induction, it's always going to be the opposite charge. You charge by touching it, so conduction. It's always going to be the same charge. And if you do by friction, you're always going to get opposite charges. Okay, so which of the following best follows the relationship between electric field, so E with a little vector arrow on it, so that's my electric field there, and the distance from the source charge. So this is more or less a point charge system. So if you remember correctly, for the formula for this, it's going to be KQ over R squared. Now the key is that this is R squared. So also it's going 1 over, it's on the bottom in the denominator. So these are my two variables. We got Y here, and then we got our X here. Now the thing is, this X here includes this kind of one that's sitting on the top here. So all of that is my X. So this R has got to be on the bottom. So it's not going to be these two. And you can see they try to straighten the graph for us. It's going to be 1 over R, but it's also 1 over R squared. So that one there, this one doesn't look good, so it's going to be C. Now, if they didn't straighten the graph itself, which is R on the bottom, would more or less look like this. It'd be an inverse relationship. As R increases, my electric field would go down. So they've done the 1 over and squared it to straighten the graph for us, and you can see that nice little straight lines here. Okay, a small object. So you can see K here is at a positive charge of 3. So this K, a positive charge. I'm just going to write that here. That'd be useful because eventually later down here, they tell us the large object is plus or minus 10 microcoulombs. I'm not too concerned about that right at this point. I'm just going to put that there. So this is a positively charged object of 3 microcoulombs. Experiences an electric static force of 6.2 times 10 to the negative 2 newtons when placed at a certain distance. I don't know what that distance happens to be. There's a little D here, which we might have to find. I don't know why I said D. Most of the time in this situation it's going to be R. Okay. Now it says here, determine the magnitude of the electric field and the direction as well. Now the key is it's a repulsion force. So this force, if I were to draw a free body diagram, is going to go this way. Okay. So that's important to help us determine what the direction is. So our electric field, we pull out your formula sheet. My electric field is, if based on what information that we have here, so we have the Q, we have the Fe, is going to be Fe divided by Q. Because remember, electric field is newtons per coulomb. It also has a direction to it, but that's the units of it. So it's the Newton per coulomb. It's just on the formula sheet too. So we're just going to put our 2 numbers in here. Our 6.2 times 10 to the negative 2 and our 3 times 10 to the negative 6 coulombs. You got to make sure those are regular coulombs when you do this. We got regular newtons there, which is in scientific notation. So I'm just punching my calculator right now. What do we get for our electric field? So we get about 20,666, about 3 sig digs, so 2.67 times 10 to the 4 newtons per coulomb. Now I do want a direction here, so you can see from the picture, because I got a nice little picture, I can go left or right here. So the force is to the left, no, sorry, to the right. I don't know what I'm talking about. To the right, that's the force. Now remember to determine an electric field. So if I want to know what the electric field is it going in towards this object or is it going away from this object, right? So it's coming out of this object in all different directions. One of these lines is going to pass through K. Now remember how to determine these lines. The lines are determined by the direction a positive charge would move, right? Because this is a positive charge, it's right here, it's a positive charge. The field is in the same direction as the force. So that's the field there. So all the fields are coming out from this object because that's the direction this object here is moving. So my field is going to the right. Okay? Because it's a positively charged object, it's being pushed to the right, and the field is the direction a positively charged object would move. Awesome. Now, what we just determined, because we determined that this to be coming out from this object, so we got all these field lines coming out from this object, the type of charge this is a positive or negative, has to be a positive charge, right? Because there's a repulsion force too. So you also think of that. If this is being repelled, this has to be a positive charge, so its fields are coming out. So that's one way to determine this direction too. So if the larger one is a positive 10 now, because we decided that this is a positive charge, determine the distance. Place it doesn't really matter if it's positive or negative for the formula. Now, what they're looking for, they determine the distance. They're looking for R. That has to be placed to get this force. So we're going to look at the formula. The formula says Fe, absolute value. So the direction and the charge magnitudes, the signs of the charges doesn't matter. K1, KQ1, Q2 divided by R squared. So I'm going to rearrange this for R squared started off with. Then we're going to take the square root, get R by itself. Oh, excuse me. KQ1, Q2 over Fe. Okay, so we got all these numbers. We just plugged them into my calculator. I'll just write them out. Remember, our K value is 8.99 times 10 to the 9. There's a bunch of units to it. I'm not too concerned about that at this point. 10 times 10 to the -6 coulombs. 3 times 10 to the -6 coulombs. Those are my two charges. Let me put a line there. And put another vinculum right there. And 6.20 times 10 to the -2 newtons. Okay. Let me just scroll down here. We've got all the numbers we need. Punch your calculator out here. 8.99 times 10 to the 9 times 6 times 10. Why did I go 6? 10 times 10 to the -6. 3 times 10 to the -6. Divided by 6.2 times 10 to the -2. Pretty reasonable number. Take the square root. So once you take the square root, you get 2.09 meters. As long as you put all the units in proper, you should get meters out. Because this is in newtons, these are coulombs. If you look at the constant, there's meters in there. And so we get out meters as well. Looking pretty good. Okay. Let's scroll down here. So they just want to know, at this point here, what's the electric field? What's the direction of the electric field at that point? So K is a nice positive charge. That's going to be useful. M is positive, and L is a negative charge. So what I know about K is all the field lines, my electric field lines, are going to come out of K, right? Because it's positively charged. M, the same thing, out of M. And P, all the electric fields are going to point towards them. Remember, this is kind of the incorrect way of drawing them, but this is kind of useful up here. So at point P, maybe I should color code this. Okay, so K I'll use red. So the arrows are coming out of K. Nice little red arrows. So at point P, caused by K, so if I were to kept on drawing arrows that are pointing out, at this point here, there'll be an arrow pointing away from K in that direction. Okay, that's caused by K. Okay, so the other one, M, is coming out as well. I'm going to draw that green this time. So that's also coming out because it's positive. So there'll be an arrow coming out of P pointing away from M, caused by M, right? So these two, if you look at them, this is 3 and 2. There's a certain distance here. They're about the same distance. The charge is slightly off, so maybe the M1 is going to be slightly smaller. It's about 2/3 of the size right about there. Okay. Now, that doesn't really matter because L is significantly closer, a lot closer. So this distance is close. Its charge is bigger as well. So there's an arrow pointing through P right now that's going downwards. A nice big arrow going downwards. So mostly, if I want to go down here, you want to know at point P, the field is mostly going which way? It's mostly going down towards the bottom of the page because how close it is to L at that point. All right? Now what we're going to do with these three charges, or these three spheres, is we're going to take these three spheres, touch them, and separate them based on what we're doing here. All right? Oh, so separated without grounding. Okay, that was my mistake on that one. Oh, I should probably fix that typo. No, with grounding, because if it was grounded, everything would just be neutral at the end. Nothing would work. Okay, we touched together, separated without grounding. So I got to fix that. Okay, I'll fix that later on. So K and L. So let's just start off here and I'll put down 3, positive 3, negative 5. These are all x's. I'm not too worried about the x's. And positive 2. Okay, so K and L are going to touch. So when K and L touch together, we get a total of negative 2 x's, and then they separate to both to be, now this is what I did, I'll write this out here, K, L, and M. So K and L are now both going to be negative 1 x each. M doesn't change, it's still positive 1. Okay? Now what we're going to do is we're going to touch K and M together. So K and M are going to add together. We get positive 1x when you add them together. When they separate, we get positive a half each. I'll put a positive in front of this one. Okay. Now L and M are going to add together. So you got 1 and negative a 1. So that becomes negative a half, right? Makes sense. Okay. So K didn't change because we're not touching K in this one, but L and M, you're going to divide this by 2, so I get a quarter. So after I divide it by 2, I get a quarter. And then hopefully that's one of our answers. Yeah, you can see down here, D is our answer. Oh, that's kind of weird. D flopped around there. Okay, so remember that's what we're doing. We just add, divide by 2, add, divide by 2. They don't do it too much other than that. Okay, so for question 7 here, we're going to take our charged objects, 1, 2, and 3. And look at, as you can see here, I want to determine the net electric force on 2 caused by the other 2 charges. So let's say 1 is a red force. So they're both, 1 is negative, 1's positive. So what's going to happen between these is they're going to retract each other. So there's going to be an electric force this way. All right? And then between 3 and 2, because I'm looking for what's happening on 2 here, they're both positive. Okay, since they're both positive, what I'm going to do now is they're going to repel. They're closer. It's a smaller side. I don't know exactly the magnitudes, but I know there's going to repel. Okay, but there's other forces here too. If you want to think about what's happening to 3, it's getting repelled as well. And I here, 1 is getting repelled, or sorry, 1 is getting repelled that, or attracted this way, equal and opposite forces. But they are there, but we're really worried about what's happening on this guy here, right? What's happening here. Okay, so if I can find those 2 forces, I can add them together. Because they're both going in the same direction, I'm allowed to add them together. I want to find the force, I need the direction, so it looks like everything's going to be going off to the left there. So KQQ over R squared, I'm going to do this twice. I'm going to do it for 1 and 2, and then I'm going to do it for 2 and 3. I'm going to get both these numbers here. Okay, so I'm not going to bother showing the substitution here. You guys can do that. Remember, micros have to be changed to -6. Centimeters have to be changed to regular meters, so 10 to the -2. So I can just punch these in. Now, I'm not too worried about the negative and positives because I know the direction from the picture. So by putting the -6.5 in my equation, I might run into a problem like, oh, it's negative. It means it has to go negative direction. But we know it's going left because of the picture. So why do I need the negative in there? You never do, because you get absolute valued anyway. All you get is the absolute values. So if you do get a negative out, just turn it positive. Okay, so take my 2 charges here. What do we have here? Sorry, excuse me. KQQ, yep, divided by 20e to the -2 squared. Okay, so this first one I get 5.113 ... newtons. Okay, I know it's going left, so I can write left here. Okay, let's put that there. And I'm going to do the same thing with the next one here. Hopefully you've done this already. I'm doing 2 and 3. Hopefully you're getting bored of me typing stuff in my calculator. Boop, 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 boop. Squared. Make sure you square that. Most common mistake is to miss the square. They were closer, like half the distance. Yeah, so it's a quadruple this, because you halved, it's quadruple the force. That's also a third, so it is bigger. It ends up being 8.8102 to the left. Okay, I should spell left correctly. Since they're both going left, I'm going to look at my net force. So remember, our net force is just the sum of all the forces. There's no x and y's here because everything is just collinear with each other. They're both going left. So my net electrostatic force on this is just going to be the addition of these 2 numbers, 5.113 plus If I just said left is positive, yeah, I could just leave these as positive numbers. Let's just say that up here instead. Left is positive. I'm going to add these together. I don't know how precise my number will be, but it'll be close enough. I'm looking for 3 sig-digs. So 13.9 newtons to the left. And there you go. Looking pretty good. Boop, boop, boop. You probably could say like 180 degrees. If you want to go standard position, you could. But just left and right is just fine for this type of question. Okay, so in this question here, we want to do what's my electric field, not force, but field at point B. And the reason I can't do a force here because there's no charge there, right? But there is a field there caused, just like the question with all the arrows from K, L, and M. There's a field here caused by both of these, and that field is going to add together, right? So if I were to say the field caused by I here at this point, I'll call that 1, I guess. Because it's negative, the field that's around this, all the little arrows are going to be pointing towards it because that's the direction a positive charge would move. So the field caused by I going through this is going to be going towards I. And the same thing with 2, because all the little fields are around him are going to be pointing towards him. The field at this point, it also is going down towards 2. So I got some X and Y here I'm going to have to deal with. So first of all, well, maybe I should use different colors here. So 2 is red. Let's use that instead. Okay. So I'd have a field going down caused by 2 there. So I have some X and Y. So for charge 1, the field at that point is going to be KQ1 over its distance squared. Okay, and then for charge 2, his electric field up at this point here is going to be KQ2 over its distance, 10 times 10 to the negative 2 squared. So I'm going to find both of these fields. I'm going to deal with the X and Y's in a bit. So 8.99 times 10 to the 9 times 2.5 e to the negative 6. I'm not worried about the negatives again, but I'm worried about that I have to square this bottom number. So I get a field, a pretty big field, 2247500. Remember, these fields are newtons per coulomb. And they're going to do the same thing with the blue one over here, or 2, I guess, or 1, sorry. K.9 times 3. It's a bigger charge, but it is further away. Twice the size, so it should be a smaller number. Yeah, slightly, well, quite a bit smaller actually. So 674,250 newtons per coulomb. So 2 million versus 600,000. Okay. So what I know about these two forces is that they have components now in X and the Y direction. Because they're not collinear, we're going to have to worry about that. But it's nice to know that this one's going straight down. I need a sign convention. I'll say up and to the left are positive. So like north is positive and east is positive here. I put this compass here because that's how we're going to answer a question. We're going to need an angle. So either standard position or northeast, southwest. And because I gave you the northeast, southwest here, I can use that part. So I got negative 2247500, so negative 2 million newtons per coulomb downwards in the Y direction. And the reason that's all there is because I have no X component. Now on my other one here, it's all X. So it's going to be negative 4722. And then I have 0Y because it's going straight across here. Oops, sorry, you can't see my cursor sometimes. So it's going straight across while the other one's going up and down. So that's why it looks like that. So we're going to go down here now. Is I'm going to do a net. So my net, remember what our net is, the sum of all the x's and the sum of all the y's. So I'm summing my x's and my y's. I'm not going to use a curly bracket here. I'm going to use my sigma notation here. Sum my x's, sum my y's. So my x's is just that number because that's plus 0. And my y is just this number because it also is just plus 0. Okay, so once I have my x's and y's, I'll redraw my triangle to represent this, and then we'll have to use a little bit of trig to find out my hypotenuse and stuff. I'll just draw a little bit here a bit more. So it's up to you to decide which one do you want to use. Do you want to use your x first and then your y, or do you want to go your y first and then your x? So if I did my x first, it would look like this. Then I'm going to go my y down here. I do my y considerably larger because it is a larger number. I'll label my sides here. Okay. And then what I'm looking for is my hypotenuse. I'm looking for this number, which just happens to be going this way. You notice that I drew a dot where it started. I drew an arrow towards where it ends because that's what I'm looking for. I'm looking for this angle as well. I'm not trying to find the angle down where this part is. I don't want that angle. I want the angle that's up here. Okay. So to find this question mark, that's just Pythagorean theorem. It's going to be the square root of the x squared plus the y squared. Punch in my calculator. I got my numbers in my calculator already. You notice that when I square these numbers, they're just going to turn positive anyway, so what's the point of typing them? Boop. So my hypotenuse, I might as well put this in sig digs right now, so 3 sig digs. So 2.35 times 10 to the 6 newtons per coulomb. And then I'm going to want to do a direction here. So to get my direction, my theta, I'm going to go tan inverse. Because the way I drew this picture, I'm going to have to go y over my x's. If you drew your picture the other way, you would have x over y. You just have another, you'll have a different number, but remember they would add up to 90 degrees. So 2247500 divided by 4250. Sweet. You get 73 degrees. 73.3 degrees. Let's just put 73 degrees because that's the nicer way to write that. Now I have to decide, because I had northeast, southwest in this question, that this is going to be south of west. If you drew your triangle the other way, you would have this answer instead. You would have 90 minus this number. You would have 16.7 west of south. Ooh, I said south, but I wrote down west. There you go. There you go. So it'd have one of those two, but your magnitude would always be the same. So it'd be this 2.35 times 10 to the 6. Okay, so all of that there is your answer. There you go. Yeah. So let's try out this next one here. We got parallel plates that are 3 centimeters apart. So here's my parallel plates. They are charged by a specific battery. That's 44 volts. The parallel plates. They are 3 centimeters apart. Now, I like this question because it's kind of a trick question. What we know about all of the space in here, like all of this space in here, this electric field that's in here, that is a constant number. Right? It's constant. No matter where I am in this field, it's always constant. Always the same, no matter where I am. So if I am 1 centimeter plate away from the positive plate, in this case, the positive plate's on the bottom. If you forget the rule, the shorter end is where the electrons come out of. So the electrons are going to be piling up on this bottom. Like you could, technically there's a rule where you can draw this kind of weird arrow here, and that's the direction electrons are going. Okay. So if I'm 1 centimeter away from this plate, I'm like 1/3 of the way up here, like here. Because my E is constant, it doesn't matter where I am. If I'm 1 centimeter here, from 1 centimeter down, right in the middle, doesn't matter. The voltage will be different. The amount of energy at that point, depending on what charge is there. Because as you move through the plates, the full distance is 44. Halfway through, you'd have half the energy. So you have 22. If you're 1/3 of the distance up, you have technically you'd have 2/3 of the energy depending on which way you're going through the system. But we're not concerned about it. We're just worried about what's the electric field strength. So this 1 centimeter, it's like a red herring. It's not useful for this question because the field strength is always the same, and you calculate it by going V over D. And V is 44 volts, and that's the whole plate system. So you have to use the distance between the whole plate system. I'll change this to meters when I do my calculation here. So 44 divided by 3 times 10 to the negative 2. I have no idea why I put this line here, so I'm just going to erase that line. So in my calculation here, I got 3 sig digs. So 1.47 times 10 to the 3 volts per meter. I'm saying volts per meter because that's the formula I used. This could also be newtons per coulomb because it is an electric field. Remember, we showed in class that they are the same thing. You just break up the units and they match each other eventually. So it doesn't matter where I am inside the parallel plate system, I will always have this same electric field. So that number is not needed. Oh, not needed. All right, it's just there to confuse you. Okay, so an oil droplet here is suspended between 2 plates. That's nice. That means my F net, because it's suspended, is 0. My acceleration is 0. There's a bunch of stuff in there. The key is if I have an oil droplet here and I draw a free body diagram, which is gravity going down, the force going upwards has to balance this out. In this case, it's electric force. So the magnitude of my electric force has to be equal to my magnitude of my gravitational force. So mass times gravity is equal to my electric force, because we talk about parallel plates. Whenever we talk about oil droplets, Millikan's experiments, it's all about parallel plates. So the only formula I'm allowed to use here for force is, I can write on this side over here for you. This is the only formula I'm allowed to use for parallel plates and force. The other two formulas, or the formula that's 2 up as a force in it, that's for point charges. So Fe, if I rearrange that, that's E times Q. Okay. They give us the charge, that's nice. They give us the mass, that's good. Calculate the electric field. So I'm just going to take this formula and just rearrange it. So divide the Q over, try to get my electric field by itself. I'm not going to show the substitution. All the numbers are there, so we're just going to plug the numbers in. They're all in kilograms. Remember, you use 9.81 for your gravity. Assume this experiment was done on Earth. And punch in the calculator. Oh, here we go. Electric field. Oh man, put 2 sig digs here in my coulomb, so we're going to do 2 sig digs. I like to keep it 3, but let's do 2 sig digs. 5.4 times 10 to the 4. And electric field. Volts per meter, newtons per coulomb, up to you. I'll just go newtons per coulomb in this one. There you go. It's nice to know if there was a direction here. It doesn't specify if the charge is positive or negative, so I guess I'm just stuck with the magnitude at this point. That's fine by me. Let me just save this. 2 seconds here. Okay, so 2 oppositely charged parallel plates you can see here, and a positive, and an alpha particle is traveling between these two. Now, what we know about an alpha particle is that it is a positively charged object. It's positively charged by 2 elementary charges. You can find that on the formula sheet. Sorry if this is backwards, but right here at the top here, I can go a little bit closer. My alpha particle is 2e, and I also know the mass here. So the mass of this, and what it means by 2e is 2 times the elementary charge. The elementary charge is times 10 to the negative 1.6 times 10 to the negative 19. That was discovered by Millikan in the oil droplet experiment. Talked about the very last day before that break, right? Before the lockdown and the quarantine happened. And then we also have the mass here. Let me just write that down. That's the right one. Yep, looking pretty good. So we know what an alpha particle is. So I have that information there. That might be useful. So what's happening here is that this alpha particle is traveling between these two plates, and just before it reaches the other side, it comes to a stop. It just comes to a rest just before it reaches the other side. Right? Just before it reaches, because what's happening is it's going to slow down. It's going to be attracted towards the negative plate, but repelled by the positive plate. So it's going to go up, 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 hit the blade just before, and then start coming back down. Hey. So that means the final velocity right here, just before it hits the plate, is going to be 0. Okay? If they tell us the initial velocity, do they? Oh no, that's what we're trying to find in this case. We're trying to find how fast does it have to be going just so that it does that. So it just comes up here, touches the other side, maybe goes in the plate, but if it doesn't, it'll come back down and accelerate back down. Kind of just like projectile motion. I don't have my pink calculator. I can't throw it behind me here. It'd be awesome if I could. So, but it's not going to be, there's no horizontal motion. It's going straight up and then straight down. So determine the initial speed. So I want to know what the initial speed is. I know my final speed is 0. So I'm going to have to find a few things. What I know from the information that we have this distance is 4.5 times 10 to the negative 2 meters. So we have our distance. To find this using kinematics, remember kinematics, I either need to know my acceleration or my time. I need one of those two things. Help me solve this question. So what are we going to do here? So we have the voltage between these two plates. So I know that this is 120 volts. That's my delta V. So because it's moving completely between these plates, it's going from one end right to the other end, it's going to change by the whole voltage. If it only went halfway, it'd be changing by only half the voltage. So I'm going to be using this voltage over here. So this is a very important number. I'm going to be using that. We're going to be using this whole number because it goes from all the way across. Right? So it makes from one end all the way to the other side. So I'm going to be using the whole thing. Okay? That might be important. Well, I wouldn't give you two otherwise. So we need to find the acceleration. To find acceleration or time, I think to find the acceleration might be easier. Acceleration is equal to F net divided by mass, because I know the mass, 6.65, I just need to know the F net. Now, F net, because this, most of the time, because these are alpha particles, you look at the mass of this is times 10 to the negative 27. Probably gravity could be ignored in this situation. It's negligible. So really the only force that's acting on this electron as it travels, or sorry, not electron, alpha particle, is a force of repulsion from the top and attraction to the bottom. So this electrostatic force pulling it down. So I'm really just dealing with Fe. Okay, so to find Fe, I look at my formula. Oh, we had that. The previous equation, the only formula I was allowed to use in that situation because it's parallel plates, is E times Q. Okay, so I know my Q and my M, but I need to know my E. So I need to look at a formula for E. Oh, I have a formula for E. So I can find my electric field by going delta V over delta D. I'm going the whole distance. The whole distance. I'm going this whole distance. So that means I'm changing this whole voltage. So I'm going to use those two numbers together down here in this spot. Times my Q divided by my M. So in the brackets there, I'm going to have 120 divided by the 4.5 times 10 to the negative 2. That's in meters now. It's in volts. I'm going to times it by my charge, which is 3.2 times 10 to the negative 19 coulombs. I'm going to divide it by my mass. You could do the step by step, like find the electric field and use that to find the force, and then use that to find the acceleration. I'm just going to do this one step. Actually, my calculator, I'm going to do multiple steps because my calculator is not as advanced as most. Not like I'm sad about that or not. Okay, so let's see what we have here. So we have an acceleration of 1.28 times 10 to the 11 meters per second squared. So quite a huge acceleration, but the problem, there's a deceleration actually, but it doesn't really matter about that. Now it's decelerating at this rate. So that means my acceleration is negative. That's going to be important for So my force is down. My distance is this direction. Let's say up is positive here. It may not be that important. We might get a positive or negative number. We're just really worried about what's the speed, not if it's positive or negative. But it's a huge acceleration. But that means the time probably is a really small amount. I'm not too worried about time either. Okay, so we look down at our formula here. What formula does not have time in it to find my VI? I flipped over my formula sheet for some reason. Oh, we have VF squared formula. VF squared is equal to VI squared plus 2AD. It's already rearranged? Oh, not technically. I guess not. I thought it was going to be already rearranged for VI, but it's not. So we're going to rearrange for VI squared. So it's VF squared minus 2AD. That's why the minus there is kind of important, because it made negative negative. We're going to take the square root. And we'll see what happens here. So our VF 0. Okay, so it's really just a negative negative. So it's 2 times my acceleration times the distance. Sorry, I forgot to take the square root of both sides. So VI is going to be equal to times my distance, take the square root, 1.07 times 10 to the 5 meters per second. Pretty fast. But as long as that's not faster than the speed of light, we are golden here. We are golden. Looks like a pretty good answer there. Okay, question 12 here. So we have an electron kind of moving further from a negative plate. So let's think about this. So here we have a parallel plate system again. We have an electron down here. And then it's moving further away from that negative plate. So it's an electron moving further from the negative plate. So what's happening to the type of energy? So as it moves further from the negative plate, it's being pushed by the negative plate and attracted towards the positive plate. Sorry, you can't see my cursor half the time. So it's going to be pushed from the negative plate, attracted to the positive plate. So therefore, its kinetic energy is going to increase. It's going to get faster. Okay. Now, where's that getting kinetic energy from? Well, it's getting it from the potential energy, which is also going to decrease. So both those statements are true for this statement. We just had to know what's causing the work. So what causes work, and remember what work is force times distance. So the force is causing the work. You apply a force to cause work. There we go. Okay, so B is our answer. Okay. Question 13 is very similar to question 11 here. This case, they're just trying to find out what the electric potential difference is. So in this case, this stands for not energy, but this is our voltage. So that's what we're looking for. We're looking for our voltage. Now I'm going to do most of my work because I don't have that much space down here. I'm going to do most of my work in the picture up here. So again, what we know about this alpha particle, we know its mass. Just write that in there. We know its charge. It's 2 times the elementary charge, so 3.2 times 10 to the negative 19 again. Same thing because that's an alpha particle. Okay. Now, what we know is that the initial velocity and the final velocity, neither one of those are 0. They give us 2 different numbers here. So it is, it's accelerating. It got faster as we went, so they gave us these 2 numbers, VI and VF. So VI is 1.4 times 10 to the 4 meters per second, and VF is 5 times 10 to the 4 meters per second. So they give us these 2 numbers, which might be useful. So let's think about how we can solve for voltage. Now, to solve for voltage, I can either use one of 2 formulas. I can use the E times delta D formula, which is, maybe I'll just rewrite that, I'll change that. I can use this formula, or I can use this formula, the change of energy over the Q. So I can use either one of these 2. We have to decide in this question, Which one can I actually do? Well, problem with this formula, the one on this side, is that I need a distance. We have no distance. So I can't use that formula. So I'm going to have to go to the other side and think, okay, what is my change of energy? Remember we talked about this. This change of energy could be either potential or kinetic. It's whatever you want it decided to be. So in this case, because I'm changing my speed, I'm changing my kinetic energy. So to find that, I need to know what my final kinetic energy is, minus my initial, and divided by its charge. Oh, that's not too bad. To find this energy, so I'm dealing with kinetic energy because my speed is changing. All right. There's no other way to find the potential energy here. So to find my kinetic energy, I'm going to have to go 1/2 mv squared for my final velocity. And then to find my kinetic energy initially, I'm going to go 1/2 mv squared with my initial velocity. Now remember what we talked about in class, there's no way to shortcut that. We just have to do the two individual calculations, subtract them, and divide by the cube. So I can just punch this on my calculator right now. 0.5 times the mass, which we know it's down there, times the speed, this is my final speed, squared, make sure you don't forget the square. So if I want to punch that number in there, 8.3125 times 10 to the negative 18 joules minus, I'm going to just, I wonder if I can store that number first. Yeah, let's put that in A, okay. I guess I could have just went to the number up there and just changed the one thing. Oh, well. Let's do both. Okay. So this one here is the 1.5 version of this number. Should be smaller. Yeah, just a little bit smaller, but not too much. 7.48 ... times 10 to the negative 19 joules. Actually, considerably smaller. Store my B. Okay, and then I'm going to divide this by my Q. So my Q value is that 3.2 times 10 to the negative 19 coulombs. So I'm going to go subtract my two numbers and divide it by my Q value. So I get 23 and 366, 23.6 volts. There we go. Hopefully I did that correctly. If I didn't, you guys will tell me in the comments. I know you will. Okay. Boop, boop, boop. Ah, a nice little two-dimensional question. Okay. So remember what happens when somebody's traveling horizontally through plates. So like the two examples above us with the parallel plates again, everything is traveling parallel to the field. So there's only really one dimension, but if I'm traveling perpendicular to the field, this is going to travel in a kind of a parabolic motion. So it's going to travel a certain distance sideways, and that's what we're looking for. What's the horizontal distance this travels? I want to find out what that d value is there. Now to figure this one out, we're going to have to think about this as two dimensions. Just like gravity, if the force only acts one way, and there's going to be a force on this electron acting this way. If it only acts one way as this thing travels through, and it doesn't change, remember the field is constant, so why would the force change? Then it experiences this parabolic motion, and because the force is always perpendicular to its motion, it'll never change that horizontal motion. Okay? It'll never change that horizontal motion because the horizontal motion is perpendicular to the force. The force can only change in the direction that it's actually acting. It's acting parallel here, up and down, so you can only change the up and down speed. So what I know, I'm going to just create a little parallel plate or what do you call this thing? Two-dimensional question. Is that on the horizontal side, my speed is, scroll up here, 2.5 times 10 to the 6. And I didn't put an initial or final because the speed remains constant. Because the speed remains constant, I can only use this one formula. There's no acceleration. So I have to use v is equal to d over t. But over here, I do have acceleration. So I probably want to put it here, my acceleration is not 0 in my vertical direction because there's a force there. Now, to find these numbers here, I'd have to have, of these 4 things, I need 3 of them. Okay. And to find this, I need time, so I can go d is equal to v times t. So that's what I'm trying to do right now. I want this piece, so I need time. So I definitely need time over here. Because it's traveling horizontally here, it travels in horizontally, my initial vertical speed is 0. Okay, I'm most likely not going to try to find the final velocity. The vertical distance is neither 2 millimeters or 1 centimeter. It's this whole distance from here to here. So that's 1 centimeter minus the 2 millimeters that it's already on the bottom there. So I'm just going to minus this. I'm going to put this in meters. So 0.008. Is that just 8? What if there's more decimals there for some reason? Yeah, well, okay. Meters. Oh, that makes sense. Okay. Yeah. So this ends up being 0.8 centimeters because you subtract out the 2 millimeters. Okay. Acceleration. So now what I need to find is also my acceleration to do this. Or find my final velocity, but I think the acceleration is going to be easier because we already know how to do that. We have to go force divided by mass. It's my net force technically. Remember, there's only one force acting on this. If we ignore gravity, we're ignoring it. It's not gone. It's always there. We're just ignoring it for this one. So that's my FE. Now to find my FE, I'm going to have to go my E times my Q. Okay, this is an electron this time. So my electron, so I'm just going to write some information about electrons. 1.6 times 10 to the negative 19 coulombs. 9.11 times 10 to the negative 31 kilograms. That might be useful. Oh, what do we have here? We have a voltage. Voltage here of 200 volts. Now remember that this voltage is all the way across. So to find the electric field that I need for this formula that's down here, find this electric field down here, I'm going to use the 200 with the 1 centimeter. I'm not going to use it with the 0.8 because the 200 is across the whole plate, so I got to use the 1 centimeter across the whole plate. Okay. So now what we have here, if I go down to this formula, my A is equal to my electric field, which is going to be delta V over delta D, times my Q divided by my M. Now my delta V, which we decided was 200 volts, or found out. Our delta D, which is in the whole distance, so in the centimeters there, or change that to meters, sorry. My Q, 1.6 times 10 to the negative 19 coulombs, I'm going to divide it by my mass. So I didn't need I needed the mass as well, so that's good. Everything's about electrons. So this is going to find my acceleration. Let's pull my calculator. Awesome. Times divide by 1. Negative 31. Okay, pretty big acceleration here, probably because it's a really small mass. Okay, so we have 3.5 times 10 to the or 15 meters per second squared. Okay, so now we have an acceleration. It's good. We're going to take that acceleration, and we're going to use a formula that doesn't have final velocity. And if you remember our formulas for that, we're going to use this 1/2 AT squared. Now, because my final velocity is 0, this is also 0. 0 times t is going to be 0. So this formula is a bit easier to use. We just rearrange for time. Square root of 2 times d divided by a. All right. So 2 times the d. Now this d, remember this d is different. This d is the vertical distance it travels, not the whole distance of 1 centimeter. 0.008 divided by my acceleration, which I did not store in my calculator. So I'm going to just retype it out. Take the square root. Okay, so a really small amount of time, but that's fine. It's traveling pretty fast, so this small amount of time might be enough to make some significant push through here. So now we're going to use this time here. We take this time that we just found. I'm going to put that up in this formula up here. It's kind of a weird spot to put that arrow. So I'm just going to redraw that arrow. I'm going to put this up in this formula right here. Okay. So I'm just going to write it down here. D is equal to V, which is 2.5 times 10 to the 6, times this time. Make sure you use all your decimals. Times 2.5 e to the 6. So we did distance 0.0053356 meters. If you look up there, we're using centimeters and millimeters to do this. I'm just going to write this as millimeters. 1, 2, 3, so 5.34 millimeters. I just moved the decimal place 3 places because it's times a millimeter is a thousands. So I'm going to move 3 times there. There we go. So it travels 3.34 millimeters horizontally. Oh, go back down there, sorry. Cool. Well, there we go. Hopefully, as you went through that, you checked out what you got wrong, what kind of questions you might have. Come to my Google Meets throughout the day here. Ask any questions. Why did I do certain thing? Hopefully, I explained it pretty well in this video. And hopefully, you guys are prepared for the actual static electricity exam. It should be pretty similar to this. Same kind of, you'll probably see a two-dimensional question and some other things like that too. So hopefully, you're prepared for it. And hopefully I can figure out how we're going to do this test. I'll get back to you on that. Okay? See you later.